Hello guys, in this video we will learn about service discovery. So in a microservice architecture there are many applications that run in different environment, like they have their own IP address, they have their own port, their own processes running, and they communicate over the network via different protocols. Like some services use HTTP, some use HTTPS, some use GPRs, gRPC, and so on. So service discovery is a process by which a service, which is called a client, let's say, automatically finds the IP address or a network location of the server for which it wants to query for some data. For example, let's say there is an order service and there is user service. So let's say a user places some order. So an order service will require the information of the user to know which user places the particular order and to process it. So order service will require the location of the user service to fetch data from it. The location of the user service will have an IP address. For example, in this particular example, the IP address is 129.8.23.23 and a port on which the process is running, for which it can query the data. So generally the HTTP runs on an 880 port, right? HTTPS runs on 443 port. Similarly, IP address tells you the location of the service, on which IP address the service is hosting, and the port tells you the address of the process on that particular service. So it will make a call to this IP address and this port to fetch the data from user service. So to find this particular location of a service, to communicate with it, we need service discovery. So let's see why it is needed. Because our services in our world now, with the use of Docker, our services run in containers. The virtual machines were used like before Docker containers, but now all the services are running in different containers, and these can be scaled up and scaled down dynamically using Docker and Kubernetes. If you have worked with Kubernetes and Docker, you can configure auto scaling, horizontal scaling in AWS as well as in Kubernetes, right? So depending on the load, your services can scale up, scale down. On the failure, it gets terminated and all those things. Because of that, IP address can change frequently for the services, right? So for example, if a service is running in this particular IP, due to some failure, if crashes and again come up, let's say, the IP address could be different. So multiple instances of the same service may run behind a load balancer as well. For example, we may have multiple instances of a service to handle high traffic, right? And we can put them behind a load balancer as well. So if we hardcode their address in the client side, for example, if we hardcode the user service address on the order service side, whenever any failure happens on any auto scaling or something happens, and the IP address of user service changes, then our communication will crash, right? Because the location is now different, and order service will still be calling the previous location where the service is not there anymore. So our communication will crash. That is why we need service discovery to get the real-time location updates. So service discovery ensures dynamic registration and deregistration of the services. Registration when a service instance comes up, deregistration when a service instance goes down. It updates the information about service instances to in the service registry, which is a DB. We'll talk about it, and it updates the client as well about the different updates. It also helps in load balancing between multiple service instances. Now let's look into the different components that are used in service discovery. Service provider. It is a service which provides usually the REST APIs to communicate, to provide data to other services, to send data to other services. For example, in this particular example, our service provider is user service, because order service will query it for users info, right? So this will be a service provider in this case, and service consumer will be our order service, which is our next component, service consumer. Service registry. It is generally a central database where all the service instances register themselves with their details like name, IP address, port, and all the metadata that is required for different communication purposes, right? So it stores location of all the available service instances. Service location, as I have already explained, This is the location on which the service is hosted, which includes an IP address and a port. Health checker, which is an optional part. So here it makes sure all the healthy upstreams are available as part of the service registry. So it periodically checks for health of different servers, and if a server is unhealthy, it removes them from the service registry. So now let's dive deep into the architecture of service discovery. So we will first talk about the write workflow. In the write workflow, our service provider will register or deregister themselves on a service registry. So whenever a new instance of a service comes up, it registers themselves in the service registry, and whenever there is a failure or something like that, they deregister themselves before terminating the instance of the service. So this is a polite behavior, but sometimes an abrupt termination may also happen. So it is possible that the deregister will not happen so smooth. So we use health check signals as well. So there is a heartbeat we call. So there is a periodic polling from service registry. Like there is a periodic signal that goes from this particular service to the service registry, and if the signal is not received for some particular amount of time, let's say for a minute, whatever, you can configure that. Actually you can configure it for maybe three consecutive calls or maybe a minute. So based on that, if the signal is not received, service registry assumes that the service is down and it deregisters it from itself. Now let's move to the read workflow. In the read workflow, our consumer will get the IP address of the servers to which it wants to communicate. So it makes a call to register. It makes a call to a service registry to read the fetch the location of the server to which it wants to communicate. Here we can use pub/sub notifications, pub/sub behavior actually, where our client can subscribe to a particular server updates, and whenever that server information gets updated, some notifications will be sent to the client. So for example, let's say order service wants to call this user service. They can just tell the service registry that I want to subscribe to all the updates that will happen on user service location. So basically there will be a topic. It will just subscribe to that topic, and service registry will push notifications through that topic to the client, which is order service. So whenever there is any update in the location of user service, instance goes down or new instance comes up, for any update, they will just go through that topic to the order service. It will be notified in real time. The advantage of this particular architecture is, like let's say order service wants to make consecutive, let's say the traffic is high, so there can be many calls per second, right? There can be thousands of calls per second from order service to user service, right? So for each call, it will not require to get the location separately, like it will just get the updates from this topic. It will cache it on its side, and it can use it for every call. It doesn't need to query service registry every time it wants to talk to user service. So there will be a little bit drop in latency, and no extra communication will be required. Now let's see how the service discovery is implemented in different microservice architecture. There are many ways to implement a service discovery. Let's go through them one by one. The simplest way is to hardcode the service location on the client side. For example, each service is manually configured with IP and port of other services. So let's say the user's IP address is something like this. We will just hardcode this IP address in the order service in some cache or somewhere maybe. So whenever the order service will call user service for any updates or to fetch any info, it will just take the IP address from the memory, and it will use that to call the user service. But the problem here is if the IP changes, if the user service IP changes because of any scaling or something, this communication will break. It will not get any real-time updates on the service location. It will not get any real-time updates of the location, right? So it doesn't support any scaling or dynamic environments. It's basically used in very tightly covered microservices where the change in IP address of the location very rarely happens. So it's not feasible in today's architecture, because nowadays we are using microservices a lot. So I don't think anyone uses this. The another approach we can take is maybe put some configuration file. For example, it can be in some external memory, or a configuration file can be passed as an environment variable in the service, or basically instead of hard coding it in the service itself, we just fetch it from a configuration file that is stored somewhere. But it still requires manual changes, because whenever this service location will get updated, we need to update this configuration file as well, right? So here we were passing, it was getting hard coded in the service code itself, but here it is getting hard coded in the configuration file, which is external from the service but still getting hard coded, right? So any update on the location or any update in this user service will require some manual updates in this config file as well. So whenever the order service makes a next call, it will fetch this config file, it will get the updated location, and it will use that to call the user service. So there is no auto scaling here as well. So in case of if there is any mistake while doing the manual updates, the communication will break. So it is also not a feasible solution for today's architecture. Let's move to other solutions. So another solution with the service discovery is using DNS. So services are discoverable by DNS names, right? So you might know, whenever a service calls another service, they basically go through a DNS. Like the order service will call a DNS resolver, which will by a DNS name, for example, userservice.com or something like that. And DNS resolver will give a IP address to the order service. Then order service will use this IP to call the user service. So service discovery can happen at the DNS resolver side. So their services are discoverable by DNS names. Underlying DNS resolver returns an IP address to this client, which is order service. Then it will use this IP, the IP that it receives from DNS, to call the server and fetch the information. But this is difficult because this will not allow any dynamic registration or deregistration of the servers. So whenever the server goes up or down, they will not be automatically register or deregister in case of failures. So there will be no real-time updates, because DNS queries are basically cached by browser and many other levels and CDN and everywhere. So that it could also be possible that let's say the update happened, it also got updated in the DNS resolver, but because of caching that is taking place in browser or at any other place like CDNs and all, the updates will be slower. So the real-time updates are not possible if we are using service registry with the help of DNS. This is one of the big problem of this approach. So we started using load balancers. So here DNS resolver will not give you the IP address of the servers, which is like user service or payment service. It will give you the IPs of load balancers. So in this approach, each of this microservice or service will have its own load balancer. So it could happen there are multiple instances of user service, there are multiple instances of payment service. They all sit behind this load balancer, they all sit behind this load balancer, and load balancer's IP addresses are resolved using the DNS resolver. So in this flow, order service will call DNS resolver to get the IP address of a load balancer. Based on the load balancer IP, if it wants to call the user service, it will call the load balancer of user service. If it wants to call payment service, it will call load balancer of payment service. Now service discovery logic will happen here. Here it will find out what are all the healthy instances of payment service or user service, and based on that it will use some load distribution algorithm like round robin or consistent hashing that we have seen in the last video, right? You can check my video on consistent hashing. It will use some load balancing algorithm, and it will use that to call the particular instance of the service. The problem with this approach is here load balancer becomes a single point of failure, because if load balancer goes down, all the connection will break, nothing will happen. Plus there will be a lot of complexity in the load balancer. It is also responsible for discovering new instances of the servers, as well as load balancing of the traffic, right? So the complexity will increase here. Plus we have different load balancer for different services. So in this example there are only 2 services, but there could be thousands of them, right? So each service will have its own load balancer, so managing these many load balancers can be difficult. So let's move to another approach where service discovery is used with the help of service registry. Here service registry is basically a database that contains the locations of instances by a service provider. Service registry is a key value store. It stores all the service configuration and the service locations. Instances of a service provider must register or deregisters themselves on the service registry. On the startup or when it fails, it will deregister themselves from the service registry. Consumers will make query to the service registry, and they will just get the IP addresses of the server from it, and they'll call it using that. There are 2 different patterns that are usually there with this kind of approach. We will look into them now. So one is client-side service discovery and one is server-side service discovery. They both use the same approach, only the difference is whoever calls the service registry to get the location of the servers is different. So if client calls the service registry, it's called client-side service discovery, and if the service registry calls are not happening through client, they are called server-side service discovery. Let's deep dive into them. So first of all, in both the cases, here as we are having all the updates and the location information in service registry, it becomes the single point of failure, right? Because if it goes down, we will not get updates anymore. All the communications will break. So to solve this problem, we generally replicate it. We create multiple instances of it in different locations, so that if one of the instance goes down, others are available to make up for that. So replication in service registry is needed to avoid the single point of failure and ensure high availability. Let's move into client-side service discovery. In the client-side service discovery, it will look something like this. So here order service is our client, right? Because it wants to call payment service. So something like this will happen. It will go to DNS resolver. It will just go something like paymentservice.com to DNS resolver. It will return the address of service registry. So please service registry, and then it will call the service registry to get the list of all the IPs that belongs to the payment service. List of IPs because there can be multiple instances of payment service running at different IPs, right? Service registry will return all the IPs that belongs to healthy instances of this service. Now order service will use some load balancing algorithm like round robin or consistent hashing again, and it will use that to call one of the instance of the payment service. So the problem with this approach is the complexity on the client side will be more, and there will be tight coupling with the service discovery logic and the service that is there in the order service and the service registry. They will be tightly coupled, and it's also difficult to implement because there is no separation of concern, right? Like it's doing too many things. It has multiple responsibilities. So this approach is not used much actually, but it improves fault tolerance because there is no load balancer here now. Because in the previous approach, if you will see, there was load balancers and there were multiple load balancers, right? Which were difficult to manage. This is not the case here. The logic sits itself in the client, and maybe the client can have also multiple instances, right? So logic will be sitting in all the instances, and all the instances will query DNS resolver, then service registry, and then use these IPs to call the payment service. So fault tolerance is there, and slightly improve of latency will also be there because there is one less network hop. So in this case, it will first go to load balancer, then the user service, and response will be written in the same way. But here, as the IP address is available at the client side only, after service discovery, it will just directly call payment service and get the response from it. So slight improvement in latency could be there. Let's move to server side service discovery. Here, again, the order service, which is our client, it will call DNS resolver to get some IP. So it will just call some paymentservice.com something, and this DNS resolver, it will give it an address. It's actually not a service registry address, it's load balancer address. Let me correct that. So it will return the address of a particular load balancer. Here, now using this load balancer address, our client will call the load balancer, and load balancer will be responsible for fetching the locations of the server from service registry. So load balancer will make a call to service registry. It will get the list of IP. Service registry will have all the logic of finding the healthy instances and registration, deregistration, subscriptions, and all this logic will be here. Load balancer will just get query it from the service registry, and it will just use its one of the load balancing algorithm and call the payment service and fetch the data from it. So you can see the approaches here are similar. So here in this approach as well as in this approach, we are using DNS, right? Here all the approaches have DNS, and server side registry, and this load balancing algorithm has load balancer. But the minor difference between them is, in these approaches there was no service registry. All the logic was sitting either on the DNS, or the logic of service discovery, like finding the healthy instances of a service will sit in the load balancer or on the DNS. But with service registry, this logic is separated out. So there are separation of concerns. In this approach, in the client side service discovery, the logic sits outside the client. The complication is on client side because it will need to call the service registry and it will need to handle the load balancing as well. But that can also be resolved using sidecar pattern. For example, if you have used Istio, so you must have seen, like whenever a pod in Kubernetes comes up, along with the container, app container, there is another container, Istio container, right? So multiple containers can run in the same pod. So what happens there? There is a side container running along with the application container, and application container will call that side container. Side container will be responsible for calling the service registry and getting the IPs and handling the load balancing and everything. Then it will similarly, there will be a side container running on server as well. So client side container will call the side container on server side. This will redirect the call to actual application container, from which it will fetch the data, make the query and fetch the data. The response will be written to the server side container. Then the response will be written to client side container, and then on the client. So the coupling gets reduced between the service registry and the client, right? So this is also used in Kubernetes. The same thing happens there with Istio and all. So in the service discovery as well, you can see the logic of service discovery is registering and deregistering and everything sits here. Only the load balancer is responsible for getting the updated IPs and load balancing the traffic by some algorithm. So there is clear separation of concerns. Also, there can be many replications, like order service has its own replica, service registry has its own replica. There will be replicas on payment service. So like there is better fault tolerance. The problem here will be there will be more latency because there are many hops now. Many components are coming in between a call, right? So there could be multiple hops. Here load balancer can be cause a single point of failure, because if you have only one load balancer, it can cause failures, right? That could be a problem here. Okay, but the implementation become trivial because client doesn't need to know anything about service discovery. They'll just call the load balancer and they'll get the response. So it's beneficial. Now I have created a table that shows the difference between all these four similar sounding approaches: DNS based, load balancer based, client side, and server side based. Let's go through it. So in this, discovery is made by DNS resolver. In the load balancer, it is done by load balancer. In the client side service registry, it is done by the client itself. But in the server side, some proxy, load balancer, or gateway is used for that. So here in the DNS base, client talks directly to the service when it gets the IP from DNS. Here, client talks to load balancer. Here again, clients talk to the directly service instance when it gets the IP from the service registry. It will call the service registry, get the IP, and directly talks to the service instance. Here, the client talks to either use a side. If it uses a sidecar container, then sidecar. Otherwise, some proxy or load balancer. Now, here there is no use of registry in first two approaches, but client side and server side approaches use service registry. Here load balancing is not possible because either client should handle it or there will be no load balancing possible. Client usually uses basic round robin DNS. Here load balancer is responsible for load balancing, and these two approaches, as we already know, client is responsible for load balancing, and here load balancer or proxy or some containers and everything, they are responsible for load balancing. There are no health check in DNS base, and there are health checks present in all the other approaches. It is possible there, but in the DNS there can be no health checks because it's not possible with the DNS. Dynamic instances awareness, there can be delay in DNS, as we have seen earlier. There could be caching and different labels and browser and CDNs and everything, so there can be delays here. There will not be delays in these approaches, right? Because we can use pub/sub subscription method to get the real-time updates. So in load balancer scenario, load balancer can subscribe to the updates of a service, right? Whenever the location of that service will get updated, it will get real-time updates. Similarly, here client can subscribe to the topic, and in the server side again, the proxy or load balancer, whatever we are using, it can subscribe to a particular topic and get the real-time updates. So there are no delays in these three approaches. The complexity on the client side is low in DNS resolver, load balancer, and server side approach, but it is very high in the client side service discovery. Here the examples are, so Kubernetes and DNS and Route 53, like they are DNS based, because if you see Kubernetes, if you know about Kubernetes, they have their whenever a service is deployed on a Kubernetes, it creates its own domain, internal domain. For example, payment.service.cluster.ip.local. So the cluster.ip local, it uses this domain to transfer data between different services internally. Like it will has its own DNS, and it will just use that to make the communication between services. So for load balancer approach, if you have worked with AWS ALB, it can be used as a service discovery. Like for different services, you can just keep a separate ALB, and your client will call the load balancer, and the load balancer will eventually redirect the traffic to different instances of the service. In this, client-side service discovery is usually seen in Eureka and Ribbon and Consul, and server-side discovery is like with Istio sidecars and all, and Consul and Envoy. So these are the examples of server-side service discovery. Now let's move into the last part, how the registration of a service is done in service discovery. So again, there are two approaches: self-registration and third-party registration. So in self-registration, a service registers or deregisters themselves. Like whenever they comes up, they register themselves on the service registry, and whenever they go down, they deregister themselves on the service discovery. But it creates a tight coupling between the service registry and the server instances, right? Because now the service itself is responsible for registration and deregistration. So another approach can be taken as third-party registration. So a third-party service can be responsible for all these. Like it can to reduce the coupling, it can just check the which service instances are up and which are going down, and based on that it can register or register those instances on the service registry. So it will remove the coupling between the service instances and service registry. Okay, that's all for today's video. I hope you enjoyed it. Please like, share and subscribe my channel. Thank you.